Hi guys, welcome to another video by Darklink Does Math. The content in this video is geared towards 6th grade math standards. These videos are public so that my students may access this information easily, as well as anyone else looking for math help. I hope you find this video helpful. If you do not, I hope you can find what you're looking for elsewhere. There's a lot of information out there. Be aware that I'm not perfect, so there may be the occasional mistake. I apologize in advance if this should happen. So today we're going over 8.4, Solutions of Simple Inequalities. Specifically, we're going to go over the type of questions that have infinite possible answers. So we need a way to write answers for those questions. So first and only vocab term that we need to go over is inequality. An inequality is a mathematical sentence that compares two unequal expressions. So, in other words, it really comes down to comparing two expressions. All right, to do that, we're going to need to know 4 different symbols. The first one is this symbol. When I read left to right, I come to the small or pointy end of this symbol first, so this is what we refer to as the less than symbol. The next symbol is this one. When I'm reading left to right, I come to the large open end first, or the big end. So I would refer to this as the greater than symbol. The next one is a repeat of the first one. However, it's got a line under it. This means less than or equal to. And the last of the symbols that we need to go over is a repeat of the greater than symbol, but it has a line under it. This means greater than or equal to. Could be larger, could be equal. Okay, so first, we're just going to focus on the less than and greater than symbols. So our first practice problem says a bag of tomatoes weighs more than 5 pounds. Part A, find the possible weights of the bag of tomatoes. So in other words, we need to know all the answers. What could it be? Like it says it's going to be more than 5 pounds, but I want all of the answers. It tells us we're going to let X represent the possible weights in pounds of the tomatoes. Part B, we're then going to represent all of the possible weights or answers on a number line. And C, we're going to determine is 5 pounds a possible weight of this bag of tomatoes. So let's start with part A. Because there are infinite answers, obviously more than 5. That could be 6, could be 8, could be 10, 20, 30, 40. It could go on and on and on. There are infinite answers. We're going to need to write an inequality. So first, we're going to write what our answer is, essentially, from our description. It says find the possible weights of the bag of tomatoes. The description says the tomatoes weigh more than 5 pounds. So we're going to use this and translate it into our inequality. So the weight of the tomatoes, it says let X be your possible weights. So the weights of the tomato is going to be represented by X. Next, more than. More than means greater than. So we're going to use the greater than symbol. And then what is the weight, or what are the weights going to be more than? Well, more than 5. So now I have an inequality. X is greater than 5. So this is a simple way of expressing all possible answers for this entire question. So what are the weights of the tomatoes? Basically, this means anything more than 5. So I've included all possible answers in the universe by writing the simple inequality. Okay, next, part B. Represent the possible weights on a number line. So, first step, to represent this inequality, draw a simple number line that can fit about 5 numbers for a good sample. Next, determine where is your number going to go. So I want all of the numbers that are greater than 5. So if I want the numbers greater than 5, that means 5 needs to be on the left side of my number line. So I can then list all the numbers greater than 5. You have to count in the correct direction. So 6 would not go on the left, 6 would go on the right side of 5. And then you can basically count by whatever you want as long as it's consistent. I'm just going to count by ones, so 5, 6, 7, 8, and 9. And these arrows indicate that the line goes on forever. Okay, next, I need to show that the answers could be greater than 5. So I'm going to draw a circle above 5 and point in the direction of all the answers. Well, all the answers could be greater than 5. So this arrow right here is basically saying that this could be an answer, 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 this could be the weight of the tomatoes. And it could go on and on and on in this direction. Essentially, anything larger than 5. One thing about that circle right there. You can either have an open circle or a closed circle. So a open circle means the value below it is not a solution. Meaning it's not an answer. So open means not a solution below it. So the value below the open circle is 5. This means 5 is not an answer. If the tomatoes have to weigh more than 5, well, 5 is not more than 5. So 5 cannot be a possible answer. 5 cannot be the weight of your tomatoes. Basically anything in this direction can be, but not 5. So think of an open circle as, whoop, it just fell right through. It's not included. All right, one more thing. Your inequality right here and the number line. They essentially tell us two things. This inequality, x is greater than 5, and this number line to represent it, where we're pointing to all the numbers larger than 5, this means the tomatoes can weigh anything bigger than 5. All right, last part. Part C. Is 5 pounds a possible weight of the tomatoes? I kind of already discussed this. Since our inequality and our picture very clearly states and show that x, or the weights, have to be more than 5, that means 5 is not a possible weight. So we're going to say 5 pounds is not a possible solution, and you should give a reason. So why? Well, because it clearly states x must be larger than 5, or x must be greater than 5. So 5 pounds is not a possible solution because x must be greater than 5. There are many ways or places to get that answer. Again, you can go back to the description. It says it has to weigh more than 5. Our inequality that represents that says it has to be greater than 5, and our picture shows that it has to be greater than 5. We are not including it. All right, next, we're just going to do a couple basic practice problems with representing inequalities on a number line. So our first one, we're going to show L is greater than 15. So first step, draw a number line that can hold about 5 numbers. Next step, determine where your number goes. Now there is a shortcut for this. If you look at the previous example, you'll notice that the arrow points in the right direction. And if you look at my greater than symbol, it almost looks like an arrow pointing in the right direction. This only works if the letter is on the left side of your inequality. If the X was on the other side, it would not work. So, to this one, L is on the left side of our inequality, so our little shortcut will work. Our greater than symbol looks like an arrow pointing to the right. So I will automatically know to draw a circle with an arrow pointing to the right, and that means the 15 will always go, well, your number will always go below your circle. And you can just double check. If I want numbers that are greater than 15, by putting 15, will all of these be the numbers greater than 15? Absolutely. Numbers get bigger on a number line as you go to the right. Okay, just count by ones or something consistent. So we're going to do 16, 17, 18, and 19. This circle is going to stay open because we're saying L is greater than 15, not equal to 15. So we're leaving it out with a big hole. All right, next one, number 3. N is less than 100. So let's try out that shortcut real quick. I see my less than symbol. It looks like an arrow pointing to the left. So put 5 spots on your number line. And since it's going to point to the left, let's draw a circle above the last line and point an arrow going to the left. And our number will go under the circle. So 100 will go right there. Now let's just check, will this work? I want the numbers that are less than 100. So if I put 100 over here and I start counting down, will I be able to put all the numbers less than 100? Absolutely. So let's do that. I'm just going to count by ones. So 100, 99, 98, 97, 96. And again, these arrows show that the line goes on infinitely in either direction. So what does this number line again show us? It shows us all of the possible answers that N could be. N could be anything to the left of my pen, essentially, whether it's a decimal, a fraction, or a whole number. All right, one more example. We're going to start with a number line, and we're going to write an inequality for it. So we're going in reverse, essentially. So first, we're going to note that we have an open circle. And we're going to note that the arrow is pointing to the right, essentially at all of the numbers greater than this one. So we're talking about greater than something. Greater than what? Well, the circle is above 14. Okay, we're just going to choose a letter. So I'm just going to always stick with X, usually. What does X need to be? Well, X needs to be more than 14. So I'm going to go ahead and put the 14, put greater than, and then that open circle means it's not going to be equal to. So I'm just going to leave it like this. X needs to be anything greater than 14. So my number line shows that. Also, you can use that shortcut to show that, oh, my arrow is pointing to the right, so I need a greater than symbol because it looks like an arrow pointing to the right. Again, that only works when the letter's on the left side. All right, next, we're going to do practice problems involving less than or equal to, or greater than or equal to. Everything is essentially the same, except for the aspect that it could equal something. Okay, number 5. Lily needs at least 7 feet of ribbon for her crafts project. At least 7 feet. So what does the word at least mean? Or the phrase at least? At least means that or more. So if she needs at least 7 feet, that means she needs that much, or she'll be fine if she has more. Kind of like if I said, I need at least $10 to go to the store. That means I need $10, but I would be happy with more. Always. Okay. Part A. Find the possible lengths of ribbon that would be enough to complete the project. Part B. Represent the possible lengths on a number line. So first, it doesn't tell us a letter, so we're going to get to choose one. So since we're talking about ribbon, I'm just going to go with capital R for ribbon. So again, I'm going to note that we chose this, or we're going to choose this, however you want to look at it. Okay, so I want the possible lengths of the ribbon. So what does it say the ribbon needs to be? The ribbon needs to be at least 7 feet. And we're going to translate that into our inequality. So first, the ribbon. We're saying the length of the ribbon is going to be capital R. It needs to be at least. So again, at least means that number or more, meaning it could be equal to that, but it could be bigger than that. So that means we're going to go with the greater than or equal to. So it could be equal to 7 feet, or it could be more than 7 feet. She just needs at least 7 feet. And last part, our number is obviously 7. So our first answer for part A, our inequality is going to be capital R is greater than or equal to 7. Now, what does that mean? That means the ribbon needs to be more than 7 feet, or it could be equal to 7 feet. She needs 7, but she'll probably be happier if she has extra, in other words. All right, part B. It says represent the possible lengths on a number line. So, first step, draw a number line that can fit about 5 numbers for a good sample. Next step, I'm going to use a shortcut because the letter's on the left, like it should be, and this greater than or equal to symbol looks like an arrow pointing to the right. I know I'm going to have a circle on the left, and it's going to point to the right. It's going to point to all the numbers that are greater than this number. All right, our number 7 is going to go under the circle. And again, I'm just going to pick something to count by, ones. So 7, 8, 9, 10, 11. Last step. It could be equal to 7, right? So in other words, I don't want to leave out 7. It could be equal to 7. So we're going to shade in our circle to include it in our answer. So what is our number line showing us? It's showing us that Lily could have 7 feet. She could have 7.5 feet, 8 feet, 9 feet, 10 feet, 11 feet, and on and on and on. These are all of the possible answers it could be. One more reminder, a closed circle means equal to, or the value below it is included. Okay, next example. On one winter day, Helena, Montana, had a maximum temperature of -4 degrees Celsius. I know, that's what I call a nope temperature. First, find the possible temperatures in Helena that day. And B, represent the possible temperatures on a number line. So first, let's discuss this word right here, maximum. Maximum means at most. Do not go past. That's what it could be, at most. next we'll realize that it doesn't give us a letter to use. So I want the possible temperatures. So I need a letter for it. We're just going to use capital T for temperatures. And again, I'm going to note that we are choosing this number, or sorry, letter. It does not tell us. Okay, so again, it says find the possible temperatures. So I'm going to write a brief description of what it says they should be or are. So the temps are at most, and the word that it actually used was maximum. So the temps are at most -4 degrees Celsius. All right, we're going to translate that into our inequality. So the temperatures we said is going to be T. At most, meaning it cannot go past, but it could be equal to that. Like we're saying it could be -4, but it's not going to be more. I know, frightening, right? So that means we're going to be less than. We can't go past it. We could go equal to it though. So maximum or at most means less than or equal to. Do not go past it. Stay under it or equal to it. And what number are we using? -4. So our answer, our inequality is T is less than or equal to -4. The temperatures will be less than, colder than, smaller than, lower than, or equal to -4 degrees. It's not going to get past that. I know. Horrible. Part B, represent the possible temperatures on a number line so we can see it visually. So number line that can fit 5 numbers. Next, going to use a shortcut. This less than or equal to sign looks like a left arrow, so I'm going to draw a circle with an arrow going left. So essentially I'm pointing to all the numbers that are less than. My number of -4 is going to go under the circle. All right, what's less than -4? Well, -5 is a lot worse, -6 even worse, -7, -8, colder and colder and colder and lower. Last, it's equal to, or could be equal to. So we're going to shade in and make a closed circle. So our picture, or our number line, essentially says the temperatures in that day are going to be -4 or lower. All right, we're going to switch and just do some practice for plain old number lines, but it does add something. It says represent the following inequalities on a number line, then state 3 integer solutions. Solution just means what could the letter be. So for example, up here, the temperature has to be smaller than or equal to -4. So capital T could be -4. It could be -5, -6, -7, -8. T could not be -1 because that would be warmer than -4. And our story says it's going to have a maximum of -4. Now, what does the word integer mean? Integer essentially means whole number above, at, or below 0. So, any whole numbers above 0, below 0, or essentially right at. All right, number 7. R is less than or equal to -20. So first, draw your number line that can fit about 5 numbers. I want numbers less than, so I know I'm going to have a circle on the right side, and I'm going to point to all the numbers less than -20. All right, let's count numbers that are less than -20. -21, -22, -23, -24. And because it could be equal to -20, we're going to shade and include that number. So R can be anything from -20 left. So let's use that to state our 3 integer solutions. Again, as long as it's a whole number and it fits our picture, we're good. So could negative 20 be a solution that's an integer? Yes, it's whole and it could be equal. It's included. So negative 20 could be a solution. What's another solution? Negative 21. And I could use any of these possible numbers. I could even go further. Could negative 25 be a solution? Yes, it's less than negative 20 and it's whole. So negative 25 would be an example. Could negative 20 and a half right there be an example or a solution? Not an integer solution because it would not be whole. It would be a solution, but not an integer solution. All right, number 8. D is going to be greater than or equal to 100. So number line, fit 5 numbers. Because I want numbers greater than or equal to 100, I'm going to have a circle. I'm going to point to all the numbers greater than, put 100 under the circle, and count up. So 101, 102, 103, 104. And because it's equal to, I should include 100 by shading in that circle. Okay, what are 3 integer solutions? Not any solutions, but 3 integer solutions. Well, it could be 100 or larger. So I can just pick any whole numbers that would fit this description. So 100 would be my smallest integer solution possible. I could do 101, I could do 102, 103, 104, I could do 200. 200 is a whole number that is bigger than or equal to 100, according to my diagram, or my number line, that is. Now, if I screwed up my number line, it might not be a solution. All right, number 9. Y is less than or equal to 9 and 2/10. So number line, fit 5 numbers. I want numbers less than or equal to 9.2. So less than means circle on the right, arrow going left. Put your number under the circle, and you'll notice that my circle is not really above 9.2. That's bad practice. That would mean like it's 9.3 for all I know. So line up your circle. Okay, I want numbers less than 9.2. I could count by ones, I could count by tenths. It doesn't matter as long as you're consistent unless you're given guidelines. Since my question doesn't necessarily give me any guidelines, I'm just going to count by ones. So 9.2, 8.2, 7.2, 6.2, 5.2. As long as you're consistent, you can do pretty much whatever you want unless you're given guidelines. All right, it could be equal to 9.2, so let's include that by shading that circle. Okay, next, I need 3 integer solutions. Not any solutions, integer solutions. Could 9.2 be an integer solution? No. Why? Because it's not a whole number. So I need a whole number that would be here. Now, if I had not chosen, to count by whole numbers, or sorry, ones, I would have probably found one. So let's think. What's less than 9.2? Well, 9.1. Ooh, 9 would be right there, right? So 9 is less than 9.2, and it's a whole number. So 9 is a solution. If I keep going, I'm going to eventually run into 8. So 8 would be a solution. So essentially 9, 8, and any number smaller. So what's another random number that would work? 4 would work. And the list goes on and on. All right, one more example. B is greater than or equal to 23/4. So 1, 2, 3, 4, 5, and that's horrible. Let's redo that. What am I doing? Not paying attention, that's what. So 1, 2, 3, 4, 5. That's better. You should always space out your numbers evenly. Okay, I want numbers greater than or equal to 23/4. So I'm just going to go ahead and shade in that circle because I know it's equal to 23/4. It's going to go there. I haven't been given guidelines on what to count by, so I'm just going to keep it consistent and keep counting by this improper fraction. So 23 fourths, 24 fourths, 25 fourths, 26 fourths, 27 fourths. Now, these numbers don't do me any good unless I know what they mean. So I should try to figure out what they actually are. I'll recognize that 24 divided by 4, or 24 fourths, is going to be 6. So these numbers are essentially around 6, a little below and a little above. That's going to help me do the second part of the question. What are 3 integer solutions? Well, I've already pinpointed one. 6 is a solution. 6 is a whole number that is greater than or equal to 23 fourths. So if I need numbers greater than, I could immediately just say 7, 8, 9, 10, all of those numbers would work. So I'm just going to go with 6, 7, and 8. 6, 7, and 8 are all greater than or equal to 23 fourths, and they are integers, meaning whole numbers above, at, or below 0. We have one more example. Write an inequality for each number line. So again, we have the number line. Now we're going to write the inequality to match. So let's note we have a closed circle and again, like the previous example, I'm pointing to all the numbers, or it is pointing to all the numbers that are greater than 7. So I'm just going to stick with x. I want numbers that are greater than 7 or equal to 7 because it's got a closed circle. So greater than or equal to 7. So x could be 7, it could be 8, it could be 9, anything greater than. So this is going to be my inequality. I hope this has helped with creating inequalities for word problems and number lines to represent those solutions. If it has not, I hope you can find what you're looking for elsewhere. Y'all have a great day.